Hello. Right now we are in the lecture for Nanofabrication Technology course. We are at lecture 5, halfway along the course. In lecture 4, we talk about the concept for nucleation and growth, which would be the principle for fabrication of nanoparticles. Okay, and in this lecture, I'm going to give you some examples and try to explain about nucleation and growth together with examples again. In this lecture, the first examples would be fabrication of metal or metallic nanoparticles. The reason that I choose metallic nanoparticles is that within these particles there is only one element. Okay, so general synthesis technique requires basically a reduction of cation, which is metals ions in solvent, and the most popular solvent would be water. So for the reduction, metals cation would be converted or would be reduced into metal with oxidation state of 0, and usually it requires precursor, and the concentration of precursor is limited normally. The reason that we do not want high concentration is that we eventually want the concentration of growth species at the end to be low, so that we will end up with diffusion control growth. Of course, because the reaction is reduction, we need reducing agent. Okay, and at the end, this is optional, we might need a stabilizer if we choose to have steric stabilization. So we will need the polymeric stabilization or polymeric stabilizer. In sometimes reducing agent and stabilizer may be the same compound, and those are highlighted in red here. The low concentration of precursor and stabilizer would eventually give you diffusion control growth, as I explained. The first example is the synthesis of gold nanoparticles. The most common precursor for gold nanoparticle synthesis would be gold chloride, or what we call auric acid here, and sodium citrate. This is basically reducing agent. Okay, the reaction takes place at high temperature, about 100 degrees C, where water is usually used as a solvent. The concentration is in millimolar, or even diluted than the millimolar, and the diameter of particles obtained will be about 20 nanometers. This is common particles, and you can see from this TM picture that atomic arrangement is really in order, so that the whole particle is the single crystal. In this case, sodium citrate acts as reducing agent as well as stabilizer. If you look at the molecular structure of this sodium citrate, it is, even though it's not polymer, but it is still a little bit bulky. So once this citrate attach itself onto the particles of gold after the synthesis complete, then it will be the stabilizer as well. In the synthesis, let me show you a video from University of Wisconsin. Okay, so basically we prepare the precursor, in this case 1 millimolar concentration, heat it up to high temperature. You need to ask yourself, why do we need high temperature? Can we react at room temperature? The answer is basically related to rate of reaction. As we explained earlier, we want the reaction to be really fast, right? So that the nucleation takes place at the same time. All nuclei are formed at the same time. So The higher the temperature, the higher the rate of reaction. And the higher the rate of reaction means we produce all the growth species at the same time. Okay? Of course, some might also ask, why stop at 100 degrees Celsius? Can we increase the temperature further than 100 degrees Celsius? The answer is yes. But doing so is not this simple anymore, because the solvent is water. If you heat it up, and if you want the temperature is higher than 100 degrees Celsius, then you need pressure. Okay, you need to pressurize the system. In that case, it's not open system like this anymore. So once it's heated, when we add sodium citrate at the same time, you can observe the change in color. Okay, the change in color means now we have reduction of gold and reduction of gold 3+ into gold nanoparticles. If I go back again and show you this video again, you should also observe that the colors gradually change. It does not change abruptly. What does it mean? You have to understand that the change in color signifies the change in particle size. Okay, so that means when you see the color change, the particles become larger and larger. Okay, so what you observe here is not only nucleation. Basically, you observe growth. Okay, nucleation occurs within very short period of time, but what you observe mostly will be growth. So if we compare between nucleation and growth, growth is more important. Growth is more dominating process that you need to control. Now, I like you to observe this phenomena. If we obtain gold nanoparticles suspended in water and we add sodium chloride solution into the product, you can see that the color changes. What does it mean? The change in color means size of particles would be changed, right? Why does it change? Does it mean the particles becomes larger or smaller? Of course, you should have the answer right away that there is no way that the particles of gold will become smaller, because sodium chloride has no ability to reduce the size of gold. So the only choice would be the particles become larger. Why do they become larger? What about stabilization in the technique? On the left hand side, the test tube becomes, you can see that the color of the product in the left hand side here remains the same. That means the product of gold nanoparticles are already stabilized, right? What is the stabilizing technique that we are using here? We learned about two things, two techniques: electrostatic stabilization and steric stabilization, right? You have to decide whether we have electrostatic stabilization or steric stabilization. Although I mentioned in the very beginning that the sodium citrate is a little bit bulkier. If it stay on the surface, it might work as a steric stabilization. Okay, but this experiment shows you that it's not really a steric stabilization, because when you add sodium chloride into the product, sodium chloride, which is electrolyte, it can neutralize charges. Once the charge on the surface of gold is neutralized, then electrostatic stabilization does not work anymore, and that would cause agglomeration, and agglomeration give you the change in color of particles, right? The particles become larger and larger simply because of the agglomeration. So in this experiment, it shows you that the process relies on electrostatic stabilization. So we can also do other way to produce the growth species. Okay, in the previous examples, the growth species was prepared from the reduction of precursor. All right, and precursor is basically chemicals. We can do any other techniques rather than using chemicals. For instance, we can use electrochemical deposition, setting up like this in anode and cathode. Suppose if I have gold bar as anode and I apply potential over this setup. The electrolyte in the system in this case is this compound. Okay, we will talk about this briefly in a moment. It has ability to be a stabilizer because its alkyl group here can be chosen to be quite a bulky group, and then adhere itself onto the surface, act as the stabilizer. Okay, but at the same time you should notice that we have ammonium groups within the compound. Ammonium groups works as a reducing agent. So the compound here not only is the reducing agent, it is also stabilizer. Okay, so if I apply the potential, what will happen? According to the high school chemistry, setting up like this should give you ions from the corrosion of the metals. Okay, so once we apply the potential, corrosion should occur on the anode, creating cations, and cations will be driven by the potential to cathode. In the high school, we observe deposition of cation onto the cathode. The process is called plating. Okay, but in this case, if we have reducing agent in between the distance or in between before the metals reaching the cathode, that means metal ion must swim through reducing agent. So therefore, during the way, the metal ions would be reduced along the way, right? Forming metals with oxidation state of 0. In other words, nanoparticles would be formed along the way. These setups replace the use of chemicals as the precursor. Okay, we produce cations from electrochemical setup like this, but still nucleation still takes place by reaction between metal ions and reducing agent in the same manner as what we used chemicals before. Okay, and the process of growth would be the same. In this setup, we can apply the technique to the synthesis of palladium, nickel, cobalt nanoparticles. Okay, and the particle size vary depending on the strength of reducing agent here, depending on the potential that we applied here, because the higher the flux that we apply to this setup, that would give the higher the flux of the metals ion from the anode to the cathode. Alright, so in general, for metallic nanoparticle synthesis, we need precursor somewhere, either using chemicals or electrochemical setup. We need reducing agent, we need stabilizer. The stabilizer here is optional. If we use the electrostatic stabilization, we don't need this polymeric stabilizer. Okay, also the stabilizer can be combined with reducing agent as well, just as I showed you earlier. In each factor, for instance, reducing agent, if we change type of reducing agent, of course it would change the product. Okay, it's not specifically influencing morphology, but it will definitely change the product. Why? Because different reagent or different reducing agent give you different strength for the reaction. For instance, for the production of gold, like this picture or like this equation, if I change reducing agent from sodium citrate, which gives you spherical nanoparticles, to citric acid, then you see that morphology changes quite dramatically. Also, the size would be changed. If I change into hydrogen peroxide or this amine compound, the size and shape will be affected. Why? You have to understand that this synthesis is basically chemistry. Okay? When you change reducing agent or change the strength of reducing agent, the rate of reaction would be different. Okay? Different rate of reaction means you produce growth species at different rate. In other words, supersaturation level will be affected. Okay? For the nucleation steps, supersaturation step or supersaturation level will be affected by strength of reducing agent. The stronger the reducing agent, the higher the supersaturation level. You have a surge in the concentration of growth species, okay, if the reducing agent is strong, and give you the higher level of supersaturation means you get a smaller particles. But as I said, comparing between nucleation and growth is more dominant. The final shape and size of the particle is mostly affected by growth. In growth, the stronger the reducing agent, if you have strong reducing agent, that means you have high concentration of growth species. Suppose you have high concentration of growth species left for the growth process, then there will be the high gradient of growth species concentration between in the bulk liquid and on the surface of the particles that give you high flux of diffusion of growth species, and that would not give you the diffusion growth that we want. Okay. On the other hand, if your reducing agent is weak, reaction rate is slow, that means the growth species is gradually produced. In that case, the growth process will be rather slow because of the diffusion limit. And we learned from lecture 4 that we prefer diffusion limit so that we will eventually end up with uniform size of the particles. Okay. As I said, the strong reducing agent should give you abrupt surge in concentration of growth species during nucleation, and that should give you high supersaturation level and end up with small nuclei that we discussed. Okay. But weak reducing agent should give you slow reaction. In this case, for the consideration of nucleation, in that case you get continuous formation of nuclei, which give you the wide size distribution of nuclei. Alright. But if there is no secondary nuclei form, how can we do not have secondary nuclei? In this case, you have to realize, even though supersaturation occurs, there might not be nucleation if the critical size is not achieved. Remember the graph that we showed you in the lecture 4? It is possible to get supersaturation, but we do not have the nucleation as long as the energy of the whole solution has not reached or has not overcome the barrier. In that case, the size of nuclei will not be greater than the critical size or stable size. Okay, in that case, there will be no secondary nucleation form. But during this period of time, you still have concentration of growth species higher than the saturation concentration, so growth still takes place. So if we have slow reaction, that means the concentration of growth species will be small or will be low, and low concentration gives you diffusion limit growth. And for diffusion limit growth, you end up with good uniform size distribution of particles. So whether or not we have this one on the left hand side or this one on the right hand side depends on many conditions. Okay, but generally, if you ask, I would say that the control of growth step is more important than control of nucleation steps. Okay, because nucleation steps occurs only in the brief window of time. Growth species takes place much longer than that, and we have to control growth step more carefully. All right. So, as an exercise, this is examples. Synthesis of silver nanoparticles by the reaction with hydroxyl groups. Okay. If I use sodium hydroxide as a source of hydroxyl groups, the product will be large particles. If I use sodium carbonate as a source of hydroxyl groups, the product is small particles. Can you explain this? If you look closely, sodium hydroxide dissociates completely because sodium hydroxide is strong base. So you get hydroxyl groups and sodium plus 100%, right? So that means once you put sodium hydroxide into this mixture, okay, what you have would be the surge in concentration of hydroxyl groups to react with silver plus to get silver metals. All right. Of course, you get surge in the concentration of silver 0 for the nucleation steps. Okay. But if the concentration of these hydroxyl groups is in excess, that should give you high concentration of silver 0 even after the nucleation has complete. So that would give you large value for diffusion for growth species. Okay, so growth species would be in the liquid at high concentration, and that does not give you diffusion control growth. On the other hand, if you use sodium carbonate reacts with water to give you hydroxyl group as well, but the reaction here is reversible. In other words, these hydroxyl groups will be produced slowly but continuously. Okay, so after nucleation is complete, still you get these hydroxyl groups generated very slowly. If you have silver plus left into the system, then they will react to form silver 0 growth species slowly at very low concentration but continuously. Okay, so in this way we will get low concentration of growth species during growth period, and that should give you diffusion control growth. As I said, diffusion control growth is very important, and you need to achieve this one so that the size of your particles will be small. Okay, not only it will be small, it will be uniform as well. Some of you might argue that the choice of strong base should give you very small nucleation or very small nuclei. That should end up with small particles, not large particles. But as I said, growth steps is more important than nucleation steps. So even though in the first, if you strong base, you may end up with small nuclei, but you cannot control the growth at all. So you can get dramatic growth and eventually end up with large particles. Okay, so this example shows you that the growth step is more important. All right. For stabilization, if you choose to use steric stabilization, not only it can be used for prevention of agglomeration, like this picture. Okay, the green area is the nuclei or the particles that is formed by reaction. The messy line here is polymer. In this polymer, the red part is what we call anchoring group. It's the part where polymer binds with particles. Okay? And the rest of the molecules is called stabilizing group, that is used for, for steric effects. But the polymer here not only prevents accumulation, but it also influences the particle growth. Why? Because when we have growth species in liquid form like this, it has to go to the surface of the particles so that growth would be complete, right? The diffusion occurs basically because concentration around here is higher than concentration on the surface, and the concentration that I'm talking about is a concentration of growth species in liquid, okay? Not in solid, in liquid. And you see that growth species once reaches the surface of the solid, it will be incorporated onto the solid so that the concentration in liquid would be kept small. That difference in concentration drives growth species to the surface. But when we have a path like this, we have barrier from the polymer, the movement of the growth species must go through this layer of polymer, which hinder diffusion, making the diffusion to be rather difficult. So this, on the other hand, gives you diffusion control growth. Okay? Also, the polymer occupy growth sites, like here that I highlight. All the anchoring groups occupy the surface. So that means growth species cannot go to that position. In other words, available surface for the growth species to land will be reduced simply because polymer occupy those sites. Okay? That should also reduce the growth rate in the same manner. So these two factors give you diffusion control growth, which is what we want. But polymer itself may have some catalytic effects on the reduction. Some polymers helps catalysts to makes the reaction faster. Some polymer retard the reactions. Some polymer is inert. So you have to be aware that polymer may have a chance to either accelerate or decelerate the reaction rate as well. And some polymer may not anchor on the surface of particles evenly. Okay, so especially if you have crystals with facet, some face of the crystals may be anchored easily than the others. So polymer density on some surface might be higher than the others. So that means the growth on the surface that is not anchored by the polymer should grow faster. Okay, so if you have, let's say, 6-sided cube and 4-sided are not covered by polymer, only 2 sides are covered, then the growth on that exposed surface will be faster. And then that means the morphology of your particles will be eventually affected. Alright? Like this picture. On the left hand side, the particle seems to be cube or cubicles. On the right hand side, particle is no longer cube. Even though you may have the same reducing agent which would give you the same rate of reaction. Okay? This is the effects of stabilizer adhering itself onto different phases of the nuclei differently. Alright? The second example that I would like to show you is the synthesis of semiconductor nanoparticle. The reason that I use semiconductor nanoparticles is that the concept is the same, but there's a little bit more complication. Okay, first of all, because this is a compound, normally compound, the elemental composition of this particle is no longer one single element. So that means we need more than one precursor. Okay, that would add some complication in the reaction. Also, these semiconductor nanoparticles usually is non-oxide, so we need to be aware of the side product that we do not want. Okay, so in order to prevent oxidation, if oxidation occurs, instead of getting what we want, we will get oxide, which is sometimes undesirable. The reaction should be conducted in the oxygen-free environment. And then for the semiconductor nanoparticle synthesis, normally what we need is what we call capping agent. And capping agent is basically the polymeric stabilizer. Okay, this is just another notation for stabilization. The common approach for semiconductor nanoparticle synthesis is basically rapid increase in supersaturation, just in the same manner as what we discussed for gold nanoparticle synthesis. But then we need 2 extra steps. Okay, the second steps and the third steps is not required in metal nanoparticle synthesis. The second one is called aging. Aging means leaving the products for longer period of time, okay, during which oswald ripening would occur. And the third one is additional process to screen the size of the product to get uniform size distribution. In the first steps, of course, once you achieve supersaturation, it will be followed by nucleation right away. And then, as you learn, growth would also take place at the same time as the nucleation. And then, after the nucleation is complete, growth still takes place. Okay, that's what we discussed in the synthesis of metallic nanoparticles. But in this case, we need extra steps, which is called aging. In this aging, we really want crystal growth. You might wonder why. Why do we need the growth? Normally, we do not want growth at all. We want to limit growth. In this case, growth is required so that size of all particles will be similar. Okay, so if we can choose, sometimes we might not need really small particles, but we would prefer all particles to be the same size. So this second step is a crucial step so that we will eventually end up with roughly the same size in the particles. And the third one is used for screening of the size. Alright. Example is synthesis of cadmium selenide nanoparticles. This one has application in semiconductor, in LED, maybe in transistor. Okay, the 2 precursors. First, this one is precursor for cadmium. This one is precursor for selenium. The full name is rather lengthy, so I'm going to skip the name. Okay, but keep in mind that we need one precursor for cadmium source. The other one is a source for selenium. We need solvent, and you should see that this solvent is organic solvent. It's no longer water. Why? Because water gives you oxidation. If you put this precursor in water, it would oxidize to get cadmium oxide, okay, which is not wanted. Oxidation occurs really fast. So in order to get this cadmium selenide, we need to avoid oxidation. Okay. Now, the solvent would be dispensed in a container. These containers will be kept in a dry box, oxygen-free dry box. Okay. We add precursor into solvent. Okay. Cadmium precursor in one beaker, selenium precursor in another. Then take a syringe, draw solution from cadmium precursor and draw solution from selenium precursor into the same syringe. Now think about this. Do we need reaction? Do we have reaction inside this syringe right away? The answer is no, not yet. Why? Two precursors are mixed, okay, within this same syringe. They are mixed. Why don't we have reaction? You have to understand that reaction can be controlled by many things. You may control using catalyst. You may also control reaction using temperature. Okay? For this specific reaction, it's not reacting at room temperature, or reaction rate at room temperature is really low. Okay? The reaction temperature for this particular set of precursor is over 100 degrees Celsius. So it is okay that we mix them first, right? Now if I keep this precursor aside and then prepare capping agent, which is another compound, lengthy compound. Put this capping agent in a beaker, flush with argon so that there is no oxygen in the system to prevent oxidation. Heat it up to 300 degrees Celsius. This is the temperature for the reaction. Alright? If I stir and then inject this mixed precursor into the system, like so, what is happening right after injection? These two precursors that were already mixed will be introduced to high temperature environment. Okay, the temperatures that reaction will take place. So that means once this mixture experiences this high temperature, it initiates the reaction right away. So this is how we achieve high concentration of growth species, or how we control to get abrupt increase in concentration of growth species. Okay? Why do we stirring? The stirring here ensures the dispersion of precursor uniformly throughout the system, so that the nuclei that is formed will be capped by capping agent right away. Alright? As reaction proceeds, the particles will be formed. Nucleation occurs initially, following by growth. Okay, you see that the color would change. Okay, then this is the first steps of the reaction. Once the reaction is done, we will take second steps by reducing the temperature down to maybe 250 for what we call aging. Okay, and aging will be kept for quite long period of time. So the first step is rapid increase in supersaturation, as I explained. Okay, this is increase in supersaturation, initiate nucleation, and followed by growth. Alright, this step is aging, so that Oswald ripening would occur. We talk about Oswald ripening in lecture 2. Okay, remember, when we have particles suspended in saturated solution. In this case, the saturated solution means the solution saturated with growth species. What is the growth species? In this case, the growth species is cadmium selenide. Okay. In lecture 2, we said for Oswald ripening, the large particles would grow in expense of small particles, because the smaller the particles, the higher the solubility. So cadmium selenide dissolve from small particles and redeposit on large particles. Remember, eventually the small particles will be consumed. So why do we need that? If imagine you have 10 particles, okay, small particles would be consumed and redeposit on large particles. The process would keep going until all particles would have the same size, right? Oswald ripening would stop when we have the same size of particles, because when all particles are in the same size, the solubility will be the same. There will be no longer dissolution of particles. So that's the main reason we want the particles to end up at the same size. The third step is called selective precipitation, size selective precipitation. So at this point, even though we end up with the particles with roughly the same size, it's not perfectly the same size. In this case, you may have the product that we want, cadmium selenide. You may also have cadmium itself and selenium itself. That is, that both of them are undesirable. If we add methanol in these systems, what we induce is what we call flocculation. Okay, so particles will be loosely agglomerated, forming a flock. In this case, if we take the mixture here under centrifuge and drop butanol in there, what we have would be precipitation of cadmium and selenium out of the system. What is going on here? Why 1 butanol? Okay, the reason that we need butanol here is that cadmium and selenium does not have high solubility in butanol, but cadmium selenide can suspend in butanol more in a stable manner. Okay, it's not really dissolved in butanol, but it can suspend in butanol, where for cadmium and selenium they will precipitate. So if we take this clear solution and add methanol again, methanol would induce flocculation. Okay, and if we take this flock, put into the butanol, you will repeatedly eliminate cadmium and selenium. Okay, so these cycles can be used to remove impurities based on the fact that the impurities and the products have different solubility in 1 butanol. Okay, so another way to synthesize cadmium selenide is in this video. We have precursor for cadmium dissolved in some acid into cadmium solution. Alright, heat it up. Now we form selenium solution separately. Once the solution, cadmium solution, is heated at high temperature, we add selenium solution right away. Okay, if I put it back for you again, when you get the temperature about 225, we add selenium solution in this mixture. You can see that reaction takes place violently right away. If you look closely, you see that the solution turns from colorless to yellow. Okay, that means reaction already takes place here to form cadmium selenide. Okay, now within this mantle we take the solution out. Okay, the first solution coming out yellow. When you draw the solution continuously into the test tubes, you can see that the color is changing. What is going on here? First, the change in color means that size of the cadmium selenide particles are not the same, right? The darker the color, the larger the size. Okay? So what is going on inside these vessels? Keep in mind that this vessel is still heated. Okay? So that means inside these vessels, the growth is still going on, right? So nucleation is already stopped, but there's still growth going on inside. The question is, if cadmium selenide can grow bigger and bigger with respect to time in this vessel, why don't we have growth in this test tube? The answer is basically a function of temperature. When you remove this process from high temperature, there's no growth anymore because growth species stopped, right? Okay. Last one is another aspect of side selective precipitation. The one that I explained earlier is a cycle that was used to eliminate impurities. So this one would be the cycle that we use to selectively screen the size. I'm going to use example for the synthesis of indium phosphide nanoparticles. This indium phosphide is soluble in toluene and insoluble in methanol. Actually, this is not a proper word. It is particle. It's not really dissolved in toluene, but they can suspend. And in toluene, when you look in the particle suspended in toluene, it looks clear. Okay. In methanol, they agglomerate and precipitate. So if from the second step after aging, we get indium phosphide in toluene, okay, you will see solution to be clear. If you add a small drop of methanol into the mixture, then you can imagine that the solubility of the particles in the solvent would be now decreased because you add the solvent that is insoluble. I mean, you add solvent that your product does not like to dissolve in that solvent. And inside here, there's various sizes of particles. The larger the particles, the lower the solubility. Okay? So when you add methanol, that is not really good solvent for this particular product. Large particles should precipitate first. Okay? Small particles has higher solubility. It remains suspended. Large particle has low solubility. It would precipitate first. So once you have precipitation like this, if you take the clear liquid on top, remove this one, and add another drop of methanol onto the solution that you remove, you get precipitation again. Okay? Now, this time, the particle precipitate here supposed to be smaller than the particles precipitate on the first steps. Okay? And it should be more uniform. If you keep repeating, you take the clear solution out, add methanol onto that clear solution, it would precipitate another set of particles with smaller size. Keep doing that, then you can screen the size that you want. Okay? What about if we add large amount of methanol at the same time? If we do that, then all kind of particles would precipitate at the same time, and we cannot select the size properly. Okay? So, as a summary for this lecture, I gave you two examples: the synthesis of metal nanoparticles and synthesis of semiconductor nanoparticles. Basically, just to explain about the concept of supersaturation, nucleation, and growth again. Okay? So, the next lecture would still be the synthesis of nanoparticles, but it would be a little bit different techniques. See you then.